Then let's start now. We had some technical difficulties. Welcome to the online meetup about distributed graph processing with Pregel and ArangoDB. Streaming is definitely too hard for me, too hard the first time. Should have tested this before. Okay, so let's come to the agenda today. So, what's the motivation behind doing distributed graph processing, especially directly in a GraphDB, a graph database? Then I'm going to introduce the model, the theoretical model behind our what we implemented, the Pregel computing model. Then I'm going to tell you a little bit about how we implemented that in ArangoDB and how you can use it in ArangoDB, and then I'm going to try to run some live demos in ArangoDB in a cluster and show you how to run PageRank and a single source shortest path and how to integrate that with AQL. And then I'm going to tell you a little bit about strengths and weaknesses of the underlying computing model and so you can have an idea of what works well, what doesn't work well, and yeah, stuff like that. And okay, so what's the motivation behind doing graph processing? Okay, obviously, graphs are increasingly common, right? You can look at your relational data and look at it like a graph, but especially like social networks and all kinds of data is now modeled as a graph, and you can process this data with various tools, and you can gain some insight on it. And so the problem is that in ArangoDB we have a graph query language, right? You have AQL and you can do graph queries, but you can't really cover all use cases, right? You can't really. I mean, AQL is already a fairly powerful language, and you can do a lot of stuff with it, but you can't necessarily do iterative processing with it, or at least not limitless. I mean, there's, for example, like if you want to do really algorithms that operate on the entire graph at once, then AQL will be kind of out of luck at some point. And so we want to be able to perform batch graph processing, right, on the entire graph, and we could do that outside the database, right? So there are existing systems that do stuff like that. There's of course Google's MapReduce that you might have heard of, that allows you to do iterative graph processing on a huge scale, distributed. I mean, and then of course there are more specialized systems which have a computing model which is focused on graphs only, and why that is, I'm gonna talk about a bit later about why there are specialized computing systems. So there's of course Google's Pregel, which we implemented here. There's an open source implementation of that, Apache Giraffe, and there's GraphX for Spark and Apache Flink, which also has a graph module called Jelly. And so why did we not want to use that? Right, we did not want to use these existing solutions because these are mostly designed for offline processing. So you export it from your data, from your graph database, basically. You set up an entirely separate software stack with separate tooling and separate like a separate file system like Hadoop's HDFS, and separate configuration management like Zookeeper, and you have to use Java or Scala to program it, and right, you might not be familiar with that software, you might not have developers that work with these programming languages. I mean, Java is of course fairly common, but Scala maybe not. So you could. The key point here is that if you have a distributed database, then your database already includes all the required infrastructure to run more distributed algorithms. So we already, in ArangoDB, for example, we already have a configuration management, we already have cluster management, and you don't really need to run that overhead of another software stack that introduces just additional maintenance cost and yeah, all kinds of unwanted stuff that you don't really need in order to run algorithms on your data. So, and of course, so how do we do distributed processing of graphs in ArangoDB? So assuming we have stored some graph data in a cluster, right? You want to perform some complex analysis on it, like calculate ranks or whatever, right? You need a way to express that algorithm, and Pregel was developed by Google to do just that, right? And it was developed to enable iterative computations in parallel on a large number of machines. And well, it's basically designed to scale up to a more or less unlimited number. I mean, in practicality, it's of course limited, but so the idea is that you can add 100 servers and it will work just fine, and you have, of course, some amount of network overhead, but it's manageable. And the idea is that Pregel is a computing model where you can take any graph algorithm and transform it into a Pregel-conform program and run it on your existing data, just by transforming your data into a suitable format, basically. So anyway, so what is Pregel? So it's basically a message passing system, right? So you have basically a number of machines, and these machines can exchange messages. And then what Pregel does for you is it defines an API where you have vertices and edges as first-class citizens. So you have an API that where every vertex acts like a little computer and has only a local state, and you can send messages around basically along these edges and to other vertices. So, but I'm going to get to that a little bit later. So the name Pregel originally comes from the famous graph problem that was posed by Euler about and Pregel is the river that flows in Königsberg or Kaliningrad now, and so the Euler's bridge problem where you need that is, I think, unsolvable. But anyway, the Pregel is the river that flows to Kaliningrad, and that's where it's got its name from. So basically, the historical background for Pregel is the bulk synchronous parallel computer model, right? So it's an abstract model of a parallel computer that was developed at the end of the 90s, I think. And basically, you imagine yourself, you have a number of machines where you can then independently perform some computations, and they exchange messages over some kind of network that is defined to be reliable, which is very important here because that's the same thing for Pregel. And then you divide these computations into super steps. So this just means that there's some kind of synchronization mechanism where all these machines can say, all right, I've sent messages, I sent n messages, and whatever number, and now at the end of this super step, there's a barrier, and then now I have a guarantee that all these messages have been received by all the receivers, right? So I send n messages to m different machines, and at this barrier, all of these machines have received my message. And that's a pretty powerful synchronization guarantee. So you can do a lot with that. So yeah, as I said, after this, so let's just look at that image really quick. I hope you can see my mouse cursor. So just assuming these three workers, they're sending messages, right? And as I said, there's the global barrier. Every worker has to wait at this global barrier, basically, until all his messages have been confirmed to all the messages have been sent, and the receiving worker has confirmed that it has received that message, basically. So you can ensure with that all workers have basically finished their computation after one superset. So, and each super step is basically just one iteration of your computation. And yeah, anyway. So in Pregel now, there's actually each machine, each vertex acts like its own little machine, right? So each vertex can basically send messages to all other vertices, and after a super step, it's guaranteed that these messages have been received and can be processed by the vertex, by the receiving vertex. So that means that you have only local state now, because each vertex only sees its own state, which means it sees its incoming messages and the outgoing edges. So that means on each machine you have a complete graph partition, which contains just the vertices and the outgoing edges for these vertices. So you don't need any more synchronization like that. There's no shared states. There's nothing shared between machines except messages which are sent, and basically everything else is completely asynchronous. So each worker can do his computations for one iteration, for one super step, and then wait for all the messages to be received, and then say, okay, now let's do the next computation, right? Let's do the next super step. And so let's look at this really quick. So there's this algorithm called the single source shortest path, which basically just computes the distance from one source vertex in a graph to all the other vertices. So let's assume you have a graph. Each graph is initialized with, you have a source vertex which is initialized with value 0, and everything else is basically initialized with value infinite, right? So you have at the beginning, no vertex knows how far it's away from the source vertex. So in the first step, you have just these initial 3 vertices, and the right 2 vertices don't know how far they are far away they are from the source vertex. So in the first super step, the source vertex with value 0 sends this message onto his neighbors, because he only knows his one neighbor. He only sees the outgoing edge and can send a message along that edge, which is the message 1, because that's the message of its current value plus the weight of the edge. So then in the next step, the first neighbor just processes the message 1, updates his local value, because obviously 1 is smaller infinity, and then will automatically send a message to his neighbors. So the first neighbor now knows his value is 1. It adds the weight of the edge, which is 3, and sends a message with the value 4 to the second neighbor, which will then be able to update his own value. And yeah, so now the neighbor knows that its distance along the shortest path to the source vertex is 4, basically. And this of course seems pretty expensive for just a small computation. But think about a large graph, right? This computation can be parallelized. You can parallelize that to how many machines and how many like as many vertices as you want, basically. And yes, let's do a quick demo of that. I hope this works now. So I've got a graph here. I hope you can see it. So I prepared this. So this is a small graph. And that I imported into this cluster here. So I got this cluster running, local cluster with just 2 DB servers, and write 2 simple collections, some vertices, and come on. And anyway, so I've got this collection now, right? And I got the vertices here, and I've got my edges here, which are just 17 edges, and now I want to start a computation on this. So let's do it really quick. So I wanted to start a single source shortest path computation. Right, first of course I need to import my Pregel module, which let's start again here. So first I want to import the Pregel module. Right, so that Pregel module works from the Arangoshell and works just against the standard HTTP API on the Arango server. And now you can basically use that to start a computation. And let's just copy this here really quick. Yeah, right, this single source shortest path algorithm on my demo graph with some source vertex, and I want to define a field in which to store the result. Right, so now I can see there's, let's say, this is my computation ID, right? That's the Pregel job that has now run. And you can check the status really quick. It's of course already done. Didn't take a lot of time here. It sent out 11 messages. It received some messages, and yeah, everything else is basically already known. So now let's check really quick. I hope this worked. I picked H as the source vertex. So let's see. This is hopefully H. Yeah. So we see now we have the source value distance from H to H is of course 0, and then you can see that the distance from everything else is basically correct. So the distance from H to this vertex is of course just 1, and then it will just propagate on the value, its local distance along the edges. So, and you can see here that all these other vertices just received its value, and this here is basically the maximum, right? This is infinity, basically U and 64 max. So let's get back to the presentation. So where was I? So we talked about single source shortest path, and now you see, I mean, this algorithm basically works, but I mean, why do we do that? Like, why don't we do we use Pregel? Why not something else and integrate that into ArangoDB, right? So the problem with graph algorithms in general is just that they have very poor memory access locality. So I've got a nice image about this later, but so what this means that edges, I mean, there are clever ways to place and partition your graph such that it's mostly located on one machine and that there are less edges between different machines. But edges just tend to point to vertices located on other machines. So that means that in order to do a computation, you have to at some point access values on the different machines. So you have to wait for that machine to send you the value of the vertex, and you have to make sure that that value stays consistent, because in your algorithm you can't, if you want to modify that value or you want to make some decision based on that value state, then you have to make sure that that state is basically locked. So this is a problem, right? You have to either then go in and say, okay, all right, so I want to access that value and that value from a vertex on a different machine. So I need to lock that and handle that locking globally and do all kinds of stuff. With Pregel, you basically have a model that's asynchronous up until these super step barriers. So so the thing is, so you don't really need to worry too much about anything, really. So yeah, it's fairly straightforward to implement Pregel on most machines, on most systems. So additionally, the work per vertex is pretty small, which just means that, I mean, even if you want to access a value on a different machine, the work for each vertex is really, really small. So, I mean, it doesn't, so compared to the amount of time you will be waiting for values from different machines, the work is basically going to be finished in an instant, but you're going to be spent ages waiting on values. So, yeah, so that's the reason with Pregel, right? In Pregel, you just send messages, and then you basically send the message and forget about it. So it's, so you just worry about other machines. You just have to figure out as a developer basically to push state to other machines ahead of time, right? If you're still at that second point here. So basically the Pregel model requires developers to think ahead of time, think about what they're going to need in the next iteration of the algorithm. And that makes it very well parallelizable. Yeah, so and why not just use, for example, MapReduce, which is of course similar in that sense. But I mean, MapReduce from the original design, it requires you to copy all data, right? And you have to, I mean, there are, for example, implementations of PageRank that for MapReduce. But these implementations basically copy all the data between these different map and reduce functions. Like if you know MapReduce, you have the map function and then the reduce function, and depending on how you set up your MapReduce cluster, this might mean that everything is copied between machines all the time. And in Pregel, you basically by design keep the state and everything always on the same machines, and you just transfer these messages. Okay, so how did we implement that in ArangoDB? So basically, if you have a ArangoDB cluster, maybe you know how ArangoDB clusters are structured. You have these coordinators that you interact with as a user, as an application, and then you have these DB servers that basically are more or less stateless, but contain all the data. So, and each DB server contains these shards of vertices and edges. So they basically contain a graph partition. And so each DB server contains these shards of graph data. And on the DB server, there are these, ArangoDB guarantees us that the edges and vertices are placed on the correct machines, right? Because as I said earlier, in Pregel, each vertex needs to know its outgoing edges. And this means that in ArangoDB, we need to ensure that the outgoing edges are actually placed alongside the vertices on the correct DB server. So that's why we add a sharding attribute to edges for Pregel computations. And we also need that during the Pregel computation to determine if, for example, an edge points to a vertex on a different machine or on the local machine. So, yeah, anyway, so let's look really quick at the actual implementation for the single source shortest path algorithm, right? So, as I said, it's fairly simple, right? You have C++ code here, or more or less C++ code. You have the current vertex value, and this is basically the content of a function that's of a vertex program. So every superstep, every vertex will execute this program. So it's a little bit like shaders in a graphic card. So you have first you fetch your vertex data, then you have your incoming messages, which are just also in 64 values, and then you just look, is the message that you received smaller than your current vertex value, which is of course just the distance to the source vertex. And if that's the case, you find out the minimum value basically. And if that minimum is now smaller than your current value, right? That's your current value. Then then you reset your vertex state to a new distance, right? And this condition here is just for basically the initial source vertex. So if the value is 0 and you are in the very first super step iteration, then you're the source vertex here, right? So once you updated your value, your local vertex value, then you need to tell all your neighbors that your value was basically updated. So right, you look at your outgoing edges here. You iterate over all these edges. You add the edge weight, which is the distance of basically the length or distance of that edge, to your local value, and then you update that. And then you tell all your neighbors, right? You send a message along that edge with your new distance value. And then your neighbor basically receives that message in the next iteration, loops through all his messages, and then he can make a decision, oh right, I'm actually closer, I need to update my own distance value, and this cascades through your entire graph. And usually this will take as many super steps as the diameter of your graph, right? The diameter is the longest, shortest path in your graph. So let's say the graph has a diameter of 10, then this will usually just take 10 to 11 super steps, and then your entire graph knows his shortest distance to the source vertex. So you can actually look at that. That's implemented here in that link. The actual implementation is of course a bit more complex, mostly because it has to do with parsing your input documents and figuring out, okay, which vertex is actually the source vertex and all that stuff. So, and this is, yeah, so it's a little bit more complicated than just that, but the core user-defined vertex function is basically this. Okay, so how do you actually use this in ArangoDB? So if you looked at the documentation, it's fairly simple, right? You have this Pregel module, which basically has just 3 functions where you can supply your algorithm, your graph, and some parameters which will vary based on the algorithm, right? So you can check the status, which will tell you something about aggregated values. So you can have global state for algorithms, for example, which will update itself continuously. So and then of course you can cancel an algorithm or discard results. And so it's also integrated into your AQL, of course. So you can, of course, by default, the Pregel implementation will write its data back into the collections, basically, right? So it will write the data, its result data, back into the vertices in the vertex collections, and you can just query your collection just like any other collection, right? Because it is just a normal collection of documents, and but you can also just have temporary results, right? So it's just each DB server will store the data temporarily in memory, and then you can treat that like a read-only collection. And so let's assume, for example, you start the PageRank computation here, right? And you tell it to not store the data back into your collection. You instead tell it to keep it temporary in memory and then store it into a rank field, for example. You can now go in and write this AQL query where you just insert that here as an inner bind variable, right? This is just an integer basically we handle, and then this AQL query will just work like a normal AQL query, and you can filter based on rank and sort it and whatever, right? And I also prepared a short demo about this. So yeah, let's do a live demo here. So I want to start a PageRank right on my graph. So I previously did that, but just for the fun of it. So we're telling it to not store data here, right? And we want to store it in the field PageRank, whatever. you can call it what you want to, and you want to do a maximum of 25 iterations, right? Because PageRank doesn't necessarily need to converge to a value. I mean, for those of you who don't know what PageRank is, that's basically the way Google used to decide how high to rank your search results when you Google something. So how you can assign each website basically a PageRank value. So now we see the computation handle is actually this integer, and we can check the state really quick. Right, and that finished here. It took barely any time. And when we look at our graph, we can make the graph print that result here in the label. Right, so these are the PageRank values now. These are basically not very meaningful by itself, you just compare them. So, but now just let's take our handle here and make a little query. I want to filter by the PageRank value, I want to sort it, and I want to return the key of the document as well as the PageRank. Right, and then you can see there are three documents or three vertices with a higher PageRank value, and now you have a result. Anyway, oh, I actually made a mistake here. Yeah, okay, now it works. The sort worked now, I think. Okay, let's get back to the presentation here. So the driver interface is actually currently not documented, but it doesn't matter that much. So basically, there's a driver interface, a REST API, which you can get to via HTTP, just like any other API, and you can just control your Pregel algorithms with that, and yeah, it will just work. Yeah, we will document this a little bit more detailed in the future. So for now, in ArangoDB we implemented a number of algorithms, right? So we already talked about the single source shortest path here. We have something similar, which is hyperlink-induced topic search, which is similar to PageRank, but not quite. We have community detection algorithms here, like label propagation, as speaker-listener label propagation. I'm going to show you a little bit about these in the next slides. Right, you have centrality measures, which can be used for all kinds of stuff. You have you can basically rank your documents based on the structure of your graph, and this can be useful if you have if you want to have something like a social graph, and you want to figure out who's an influencer in your social graph or who transports information. And yeah, there are all kinds of applications for this if you look into it a bit more. Or, as I said, the community detection stuff, this can be used to make some pretty graphs. I wanted to do a live demo about this actually, but I didn't have the time today to prepare it properly, so I just have some quick images about this. I hope you can see this. So originally I already did a demonstration once somewhere else, but where I used ArangoDB to run this speaker-listener label propagation on the Dolphins network, which is basically just a really small, well-known network used in a lot of papers on community detection algorithms, right? So it's basically a community of dolphins living somewhere, and they recorded them interacting, and your algorithm, and it's used as a pretty popular test to check whether your algorithms can figure out some amount of community structure here. So it's similar about the Zacharies Karate Club. So this is also a classic network that's used a lot. And yeah, you can see these algorithms work fairly okay. So they're able to figure out these communities that were originally recorded right? So I think Zacharies Karate Club was actually a club or a sports club, and then they split up and formed 2 new clubs or something like that. So it's really just a demonstration. So what are some caveats of using Pregel here? So Pregel has a few downsides, right? So as I said, graph algorithms tend to have poor memory locality. So if you have some document or vertex on your machine, on one machine, and it has a lot of connections across machine boundaries, this will mean that you have to send, that one machine has to send a lot of data across the actual network, which will mean that it takes longer to complete its computations for one iteration. So maybe you have this kind of, you have a super node, right? So it's one node with a lot of edges compared to everyone else in the network, which can happen a lot in social networks. Then you might have workers which take longer than other workers. You have a lot of messages in your internal buffers. This should be stale, if there's an E missing here. So you have messages that just lay around somewhere. And so depending on this, the data might actually not be very useful anymore, right? So if you have something like the original example here, the single source shortest path algorithm, if you have one of these supernodes, the likelihood that you have a pretty good approximation about the correct distance to the source node is pretty high. Right? So either a lot of these messages that you received are useless, or you might be able to discard them pretty quickly, or you might actually have already received messages for the next super step or something like that. So it's you really have the caveat of Pregel is if you have these evenly distributed graphs, then you might run into this problem on the next slides, that you have these straggling worker machines, right? And that just means that everyone else has to wait for your straggler, and you can't process the data properly that you already received because you have to wait for everyone to finish. And so I built some experimental extension into the code, which is not documented yet, for example, but what we want to do is optionally weaken these guarantees of Pregel, and this will be introduced in the coming months publicly, maybe in the next release, but we'll see. So the idea is that basically we allow everyone to process received messages immediately, and not necessarily work on every other machine, and then allow algorithms to optionally wait on when they need to, right? So maybe you have an algorithm that has a phase where it doesn't need to wait on everyone else, right? So for example, the shortest path algorithm there was it will just naturally converge to the shortest paths, but you don't actually need these synchronizations barriers every time. And maybe you have an algorithm like that, and with that you can actually have a sort of asynchronous execution where you might be able to decrease the number of overall iterations significantly. And depending on how your graph is distributed across your machines, this might actually help you a lot. So yeah, but this is still a bit experimental. The advantage of this is, of course, that you can reduce the number of super steps, as I said, but it also has some cost, because if you send out messages more frequently and you don't wait for machines to finish, then you might run into the situation that you can't do as much buffering of messages. So but this is going to be introduced maybe later. Anyway, I think this was it for today. Please thank you for watching so far. gonna have a quick look into the chat now. Maybe there's something here. So, does anybody have questions so far? Okay, so yeah, so okay, so if you have certain vertices, you can currently not filter them with AQL, but I'm gonna work on this hopefully in the future. You can reduce the number of vertex collections basically, so you can say you just want to have certain vertices, and you want to have basically you can limit the number of you can limit the graph basically based on the edge collections and vertex collections, right? So I didn't show that, but you can specify just a list of vertex collection and a list of edge collections that you want your Pregel algorithm to run against. Yeah, I hope that helps a little bit. Anyone? Okay, if there are no more questions, you can. Oh yeah, you can run these community detection algorithms already, right? You can specify, if you look at, I already did a tutorial on this, I think. Let's just look at the implementation here really quick. So you can, for example, run label propagation here by specifying label propagation as a parameter here. And you can also specify basically DMID here and SLPA. I think it's actually in the tutorials on ArangoDB. So I did it already here. There's a tutorial where I show you that how you can use the ORCOD dataset, or the POCAC dataset, sorry, this POCAC social network with community detection, right? And you can use SLPA here, but you could also write just DMED instead of SLPA here, and you would get the DMID algorithm. And yeah, you could just use that basically for performing some community detection. And you can specify the maximum amount of output communities here. Oh yeah, how does it? So currently you need to basically add a pull request to ArangoDB because there's only a C++ API now. We toyed with the idea of adding JavaScript API, but it would just be, the problem is that you need to convert the data between JavaScript and the native format every time you change something, right? So every time you want to call a JavaScript function, then you have to convert that data, and that would be pretty slow. So so right now it's C++ only, but we want to allow people to add dynamically link libraries basically. So this will be added a little bit, maybe later, I guess. Okay. Any more questions here? Is it? I mean, okay, so if there are no more questions, I mean, you can reach me on Slack, right? And I'm always happy for suggestions for more algorithms. So if you find a bug if you find a bug in the current implementation, if something doesn't work, just Slack me. I'm always happy to fix that or help out. So anyway, thanks for watching, and yeah, hopefully see you again soon sometime.